All right. Thanks. Thank you. And thanks for making it through 3 of my talks already. Right. So this is the third and last part of the talk. So I'm going to talk about cellular Legendrian contact homology. So this is another a different combinatorial formulation for Legendrian contact homology, but now for surfaces instead of knots. And in principle, it should be any dimension. One of the advantages of this, well, first of all, it's combinatorial, so it could be input. It could be programmable into a computer, and it's also has a kind of nice algebraic topology flavor. And then the other thing is that it's local. So this is what I was saying at the first talk, that the goal is you want to find holomorphic curves, and holomorphic curves are a very global thing. Change a curve in a little piece, a little area, it'll change all over the place. But if you know that the curve lives in a small neighborhood, then you can kind of just study curves in these small little piece of space and do your count there and do your count here and so on and so forth. So it makes it, maybe more manageable. Okay. Oh, right. So that's the first part of the talk I wanted to talk about. Yeah, maybe I should write this down. So 2 parts to this talk. So first I'm going to give a definition of this cellular DDA. And then, it really depends how much time I've got, I want to do some applications of this, talking about augmentations, something called generating families, which I'll define, and maybe something called sheaves, or constructible sheaves, which I seriously doubt I'll get to, but I'll just throw it up there. Secretly, I'm kind of hoping I'll run out of time by get to sheaves, because this is something I'm only learning, it's the current work in progress of what I've talked about this lecture series anyway. Okay, so in other words, things are less sure. All right, so what time did I start, just so I know? Like 40, okay. All right. Let's just recall what we're dealing with. So, oh, right. Yeah, so for this talk, we're going to restrict to Legendrians inside one-jet spaces of 2-dimensional manifolds. This does work for Legendrian knots, but we already have a combinatorial method for there, so it's not so much worth it. And in theory, it should be for any dimension. Okay, so let's just recall. So we have, so in this case, we have the front projection. So I'm denoting that by pi f. And that goes from the 1-jet space of x to the 0-jet space of x. Remember, the 1-jet space of x is the cotangent bundle of x cross r, and my coordinates are z, x, y. And the 0-jet space is just x cross r, so I'm projecting out all the y coordinates, the momenta coordinates. In this front projection, you can so locally, pi f of L looks like the graph, looks like some kind of multigraph, some graphs of fi, functions from, well, real-valued functions. So, the traditional picture is that I've been drawing is the kind of unknot. So here's x and here's z, and we have this region here, U, and we have F1 and F2 only defined on R, only defined over U, and the graph of F1 and the graph of F2 give you this thing. Okay. The two graphs meet and their derivatives agree so that the y coordinate is well defined. Well, it's the behavior of F1 with respect to F2. So you need F1 on the differential of F1 on the boundary equals differential of F2 on the boundary. That enables the y coordinate to change at least continuously. And then you need some more smoothness, higher derivatives, and so on if you really want this to be embedded. Okay, so what are, I've kind of drawn this example a number of times because it's the easiest one, but just generally, what does what does this thing look like? So locally, looks like only not too many things. Okay, so there's this cusp that we were talking about here. No, just a cusp edge. You also have a couple of sheets can cross. Okay, so cusp, crossing. These are kind of the codimension 1 things. Then you have codimension 2. So you could be made of codimension 1 things. So for example, I have 2 sheets coming in at a cusp, and I have a 3rd sheet crossing, and then the crossing and the cusp meet. Something like that. Or you have this, well, one particular one would be a swallowtail point. Well, so a swallowtail point looks something like this. You have, the reason why it doesn't a priori seem, it involves 2 cusps and a crossing coming all together. So I have, maybe I should use different colors for the crossing. Okay, so here's the crossing. And the cusp, I'll use blue. Here's a cusp. So here I have a cusp coming in, and a cusp coming in, and a crossing of the 2 sheets below that you can't quite see. So there's 3 sheets involved. Here I just have 1 sheet, and above here I have 1, 2, 3 sheets. Another way to see this is kind of looking at one-dimensional slices, and you kind of have something like this, a little cubic degeneracy, and then nothing. Okay, so we call that a swallowtail or dovetail point. Okay, so, all right, so these are the kind of singularities. So we're going to choose a polygonal decomposition. We're going to choose a polygonal decomposition of pi x of L. So here pi x is just the projection all the way down to the base. Choose a polygonal decomposition of this. So I'll write it as a union of cells. So here I'm assuming I'm writing the cells down, but I'm also got these characteristic maps. So EI alpha is an I cell for I equals 0, 1, or 2. Such that if you look at all the crossings, so things like that, cusps, and swallowtail points, they're in this polygonal decomposition. So, in the case of a cusp, well, in this case, I would have to make one 2-cell, one 1-cell, and one 0-cell. And here I made sure that the cusp was entirely in the 1-cell. Here I would have to have a 1-cell for this guy, a 1-cell for this guy, a 1-cell for this guy. This is on the base, and a 0-cell here. Okay, so with that in mind, now I'm prepared to actually, oh, I'm sorry. Shoot. I mean to say, in the 1 skeleton. So I make sure to, I project the crossings and the cusps and the points, and I make sure that the crossings and cusps sit above 1 cells in my cellular decomposition. Of that projection. Okay, so now we can define the algebra. Okay, so label each sheet. These are what I'm calling sheets. So here I have S1 and S2. I have 2 sheets in that case. Label each sheet of this projection, of this front projection, above EI alpha as, let's say, S1, S2 through Sn, where the height of Si is at least as much as the height of Sj. So I'm never going to have a 2-cell where one sheet is above the other here, and that sheet is below the other here, because they'd have to cross, and that crossing would be a 1-cell splitting up the 2-cell. So I've got a well-defined relationship between the heights of the sheets. This is the z-coordinate. Okay. All right. Oh, and with one caveat, so do not label sheets above cells when they cusp. So actually here, in this case, I've got 2 sheets over the 2-cell and no sheets over the 1-cell or the 0-cell, because both sheets are cusping over the 1-cell and 0-cell. Okay, and let's let our algebra A be the unital tensor algebra. Well, we're going to keep it simple because I haven't done anything with coefficients or signs. So this is going to be a Z2 algebra with generators X, alpha, I, J, sorry, where alpha is in the parameters, is the things that are parameterizing the cell. And SI, right, SI and SJ are 2 sheets over E alpha. And yeah, oh, and I is less than J. So in this case, we have only one generator for this 2-cell, because there's only one cell which has 2 sheets, and I can only choose it as an ordered pair of sheets where the first sheet is above the second sheet. So I've got only one generator in this whole construction. The other cells don't contribute to the generators. Okay, so that's the algebra. For the grading, we're going to do exactly what we did when we were talking about Legendrian contact homology, essentially. So we're going to define a cyclic, in principle, but maybe z-valued. I'll call it a Maslov potential function. mu, so this goes from L minus cusps and swallowtail points to Z over M LZ, where again, so recall that, right, actually, yeah. So recall that this is the Maslov number, and it represents, you take a path in Legendrian, you project it to the front projection, you take a loop, sorry, you count how many times it crosses ups minus downs, and then you take the minimum over all such loops. And that's going to be the kind of the grading ambiguity for our DGA. Okay. Yeah, sorry, maybe I should say this. X alpha. Well, actually, X is just a formal variable at this point. So alpha denotes the cell. I guess I was calling it EI alpha, because E is the traditional notation for cell. But really, and I is just the dimension. But really, alpha is what's the label for the cell. So here, we take that label, the cell, and then over that cell, we take two sheets, where one sheet is above the other sheet. So I and J, the range of I and J depends on alpha. Okay, so we define a cyclic Maslov potential. I'm just going to define it like this, locally. So, basically the Maslov potential of a sheet above a cusp has to be one more than the Maslov potential of a sheet below the cusp. And that exactly represents the fact that when we go down a cusp, we're adding one to whatever Maslov grade computation we do. So that's all. Okay. So now I'm going to define the grading of these generators and at the same time introduce some notation. So that's not a grading yet. That's just a potential, what I call a potential on all of the sheets in the front. Okay. So, actually, I probably need more space than this. Okay. So, we define a grading on the algebra. This is going to Z mod M by the following. So E alpha could be a 0 cell, a 1 cell, or a 2 cell. Okay, and so for the notation, rather than X, I'm going to call the generators over a 0 cell, I'll denote them by A's. Over a 1 cell, I'll denote them by B's. And over a 2 cell, I'll denote them by C's. And the grading we're going to give to each of these generators is mu of the upper sheet minus mu of the lower sheet minus 1, mu of the upper sheet minus mu of the lower sheet minus, nothing. And then mu of the upper sheet minus mu of the lower sheet plus 1. And the way you're supposed to think about this, if you recall the definition for the grading in Legendrian contact homology, is, okay, imagine I'll draw a one-dimensional picture. So here's my X, which I'm just going to think of as R2, but I'll just draw it as, well, I'll just draw it like this. And here I have, maybe my Legendrian. Here's pi f of L. This is the z coordinate. And here is some polygonal decomposition. By the way, I can add cells. I don't have to make, this is not equals, this is contains in. So I can fracture my polygonal decomposition and make, subdivide it. So here I don't have any crossings or cusps, I just have, but supposing I subdivided it here. And I have like Reeb chords. This one is a minimum. So I'd have something like Maslov potential plus Morse index minus 1. This is the secret formula behind this grading that we saw. So in the case of a 0 cell, I have a minimum. So Morse index minus 1 is minus 1. Whereas the case of a 1 cell, I have a saddle. You don't see the other dimension. And in the case of a 2 cell, I have a maximum. So that's why I have a minus 1, a 0, and a plus 1. It's basically 0 minus 1, 1 minus 1, and 2 minus 1. That's the motivation for it. Anyway. Okay. All right, so that is my grading. All right, so now I have to do the differential. So again, I'm going to do it cell by cell. Okay, so supposing I have, first, I'm going to simplify some notation here. There's a lot of generators over a given cell. So let's let M equal the let's say M, equal the upper triangular matrix, strictly upper triangular matrix with, let's say, M alpha, with entry X alpha ij. So this is a collection of all of the generators over a given cell. It's strictly upper triangular because remember I'm only doing sheets, where is that? Here. Okay, so I have some 0 cell. And I have a matrix of generators. So the generators are, let's say, I'll call them A, using this notation. Okay? And then the differential is defined as dA equals A squared. And what that means is, this notation means this matrix, the ij matrix is, this notation means D of ij is summation aik, akj, where k ranges from j to I. So I'm just doing matrix multiplication to get the ijth element. Okay? Any alpha, I dropped that. I mean, I should put an alpha and an alpha and an alpha and an alpha. Yeah, any alpha. But I'll just drop the alphas because it's getting a little... Okay, now supposing I have a 1 cell. And maybe I should have mentioned this, but the 1 cells need to be oriented. So I'm going to draw 1 cell like this. And supposing I have a matrix of generators, A minus, B, and A plus, because there's a positive and negative 0 cell associated to this, then the differential of B is going to be A times 1 plus B plus 1 plus B times A minus. So actually, if there were signs in here, you would put a minus sign here. So I could just write that because plus and minus are the same thing. And this one looks a little more of an algebraic topology flavor, kind of a chain map equation. And then for the 2 cells, okay, so the 2 cells, let me just draw like a, it might be who knows how many edges. Okay, so for the 2 cell, first you have to choose an initial and terminal 0 cells. So I'll denote it V0 and let's say V1. And let's suppose, now the orientation of the 1 cells may not have anything to do with how they sit in the plane. So maybe I chose the arrows like this. And let's say this is B1, B2, B3, B4, and B5. Then the differential for this C is given by A plus C. This is the matrix sits over V plus. I guess I was calling it. well, I'll just, it's not really, so 1, 0. Plus CA0 plus, now we're going to think of two paths going from V0 to V1 and write out the chain maps that are induced by these paths. So if I go along this way, it would be 1 I plus B1. Then actually we're going the wrong way, so I plus B2 inverse, because the path does not agree with the arrow. And then finally I plus B3. Or you could go along this path. You would have I plus B5, I plus B4 minus 1. So this you're kind of supposed to think of as a differential. This is a chain map, and this is a chain homotopy between the two chain maps of the boundary. That's kind of the algebraic topology flavor of it. Okay, so that's kind of the differential. So I'm done with the lecture. No, okay, well, I could spend another hour, so let's spend another hour or so. So there's some caveats here. Oh, yeah. You just choose it. It's an auxiliary choice. Make it whatever you want. Yeah, so when I say choose a polygonal decomposition, I forgot to mention, and orient the one cells to whatever way you want. Doesn't come with, oh, no, it's not oriented, although for practical purposes, when you want to do coefficients more than Z2, you need to orient it for other reasons. So I never really think of it unoriented, but okay. So there's a few little caveats here for me to make. So when I write these matrix equations down, first of all, I'm writing them as if they're all the same size. And second, I'm writing them as if there's some sort of global basis. And neither of those are true because, for example, the first one, we don't label sheets above cusps. So over one cell, I could have 20 sheets, and over another cell, I could have 5 sheets. Or even, sorry, I could have 20 sheets over this 2 cell, and maybe only 18 or 16 sheets over this 1 cell if I had some of these pairs of sheets cusping over here, for example. So what does it mean to have B3 be in this equation? So let me make some remarks. Okay, so first of all, first I should mention, if I really want to write this with signs, to write it with signs, or more, or something like Z2, ZH2, this is kind of the most general. Actually, to tell you the truth, we can't even do that. We have to do it, just this is the most general we can do. It's not quite that simple. You need some sort of matrix of Maslow potentials. J, which looks like mu of sheet 1, mu of sheet 2, mu of sheet n, floating around here, basically out front. In the front of the left-hand side, right-hand side. Even that, we haven't proved that statement rigorously. Oh, I should mention that this is joint work with Dan Rutherford. So this is a conjectural thing to be able to do it with signs. And then another one is just modifying the number of sheets. So let's say, for example, I have, okay, well, I'll write down this statement and then I'll just draw a little example. Actually, maybe I'll just draw a picture. Okay, so supposing I have something like this. Here's A minus, here's A plus, and here's B, and I have, you know, two sheets that come into a cusp. So let's say this is like SK and SK plus 1. So these sheets continue, and over this zero cell, I only have a 3 by 3 matrix, and over this one cell, I have a 5 by 5 matrix. Then what you do is A minus in the formula for dB is enlarged to look something like in the k plus 1 row and column, you put in a matrix that looks like this. So these are zeros, zeros. So you add two columns and rows of zeros, except for you put a 1 there, or something with a sign. To enlarge, similarly, to enlarge B in the right-hand side of DC, you add all zeros. Okay. And the reason for that, just morally, is that there's going to be a read chord here that has the same index as 1. It's the degree 0 read chord over the A, but not over the B. Okay. So another modification that you have, I guess these are modifications, really. Another modification you have to do to this formula is the idea that sheets are not globally ordered. So sheet ordering is only local due to crossing sheets. So replace A or B in the left-hand side, right-hand side of D by a permutation matrix. To make ordering consistent. So permutation matrix that just permutes K and K plus 1 if it's sheets K and K plus 1 that are crossing. Okay. And finally, this one is the biggest hurdle and the real reason why we stopped with surfaces. Well, yeah. And that's because the classification of singularities of functions gets more and more complicated as the dimension increases. So I was able to draw in dimension 2, basically the swallowtail was the only interesting thing. In dimension 3, there's like about 6 of them, and then it kind of just becomes innumerable at some point. And each of those requires special attention, so it becomes kind of impractical. So even the swallowtail is difficult. So I think what I'm going to just do. Yeah, generic. Yeah. Well, to tell you the truth, you can compute it for non-generic ones, but a priori I'm defining it for generic L. But you can always take a non-generic one, perturb it and see what's there, and then just compute it. I mean, so in some of them it's practical to do because they appear more naturally in this field. But yeah, thanks for that clarifying point. Okay, swallowtail modifications. So I think because I don't know how, didn't make it to the Morse theory talk, so I don't know how much was discussed. But I'll just mention that what you do here is you follow Hatcher and Wagner's two-parameter Morse theory used for pseudo-isotopies. So they have some results studying when is a pseudo-isotopy an isotopy, not that that's relevant to this discussion, and basically it boils down to looking at not just a single Morse function, but a two-parameter family of Morse functions. And they draw their Serif diagrams, and they see these things like swallowtails, which they call dovetails, and they have some algebra, two-parameter Morse theory / Whitehead 2 invariant. They have some Morse theory, which they interpret algebraically into a kind of K-theory invariant known as Whitehead 2, the Whitehead 2 invariant. And the way they deal with the swallowtails is exactly the way that we change our differential. So I'll just leave it like that. So their algebra in Whitehead 2 invariants is exactly what we need to modify the differential in the presence near a swallowtail point. Okay, so I'll leave it like that. All right, so we have this differential, well, I have something which is allegedly a differential, so you can actually prove, that d squared equals 0, that the stable tame, well, let's say the homotopy type of the DGA is independent of the choices that were made. So for example, the polygonal decomposition, the ordering of the zero cells, the choice of the initial and terminal cell over there, the ordering of the sheets in case some of the sheets crossed. I don't know, there were various choices along the way. But then the main theorem is that this DGA is stable tame isomorphic is equivalent to the Legendrian contact homology DGA. And in fact, in the case of squares, if all polygons were squares, if all two cells were squares, this is even true like on the nose. The differentials are, yeah, what should I say? Well, maybe I won't say it. Well, I won't write that down. Okay. So, the obvious question, I'll put it down as an open question. So does this work in higher dimensions? And so what do I mean by this? Well, I mean, as you see here, you're starting in this algebraic story. If you have a two-dimensional surface, you go up to 1 homotopies. Now, if you have an n-dimensional Legendre, it'd be natural to think you'd go up to, I guess, n minus 1 homotopies. If this is a 1 homotopy, a three-dimensional would have 2 homotopies, and so on. And you just write down the equations where basically, it would look something like, d of some, I don't know, what letter do I still have left? D of some n cell is equal to summation ei ej, where I plus j equals n, with the exception where E1, if it's a 1 cell, you replace it by I plus E1. Something like that. I mean, at the 1 cell, it's always a different story because you have in any of these homotopy theories. So this would be like the natural kind of guess at what it might be. And of course, the problem is actually proving something like that. So I'll put that as a question mark. Okay, any questions or about the statement or? Yeah, replace A or B by the change of basis, yeah. Yeah, like, so for example, supposing this is where two sheets cross. And, I have C1 and C2. And so if I look at these two sheets, they're definitely ordered differently here and here. And here I have to make a choice. So if I make a choice, it's either consistent with this one or with that one. And whichever one it's inconsistent with, when you look at the differential, you'll have to replace B by the QB Q inverse. I mean, the crossing locuses can only kind of end at swallowtail points, which I kind of safely brushed under the rug. Oh, you mean, oh, right. No, I guess you could have a circular thing. No, but it'll be, yeah, it'll be consistent. Okay. All right. So let me just give an example. So I was kind of already doing. Let me do the basic example and then a slightly more interesting example. So supposing I have my favorite example, this unknot, okay, and I choose something that looks like something like this. So I just have A, B, and C in some order. Okay, so now, so A and B, oh, that's not really lined up. Okay, so A and B are zero-dimensional matrices. C is just this matrix. And so when I want to write down this formula, what was I calling it? 1 and 0. First, I have to choose an initial and terminal point. I only have 1 point, so I'm just going to use the same point. So this is the initial and terminal point. Second, I have to take a path. Well, here I have one path, I plus B. The other path is actually just going to be the constant path, I. So this is the constant path. And so now, this matrix is going to be 0, 0, 0, 0. And these two matrices are going to be 0, 1, 0, 0. So if you actually compute this out, you get D of C1, 2 is 0. Not too surprising. Right. Okay. So, one problem with this is that it's hard to compute by hand because the number of generators is quite a lot. You have matrices over cells. You can see it's like order n squared. But so a by hand computation is less practical. But you can still do some. So let's suppose, so if you look at this, Legendrian sphere, okay, so this is equivalent to something like this. So I have a long cusp edge, okay, which is equivalent to something like this. So again, I have this long cusp edge going, I don't know how to draw this. I guess it's going behind here, and then one's coming out here. And then the question is, supposing, what if I just try to push this one through there? Okay, so this is a Legendrian isotopy, and this is a Legendrian homotopy. And the question is it a Legendrian isotopy? I mean, the move by itself is not an isotopy because I have an immersion point at a singular moment, but maybe there is some other way I could kind of push it through. So to show that it's not, let's just look at the DGA of this guy compared to the DGA of that guy and see that they're different. So in this case, I'm going to imagine that this one is smaller. Okay, so I have a cusp edge here and here, and I also have a crossing, a circle of crossings here. So all of these blues and reds have to be in my polygonal decomposition. So let's draw the projection of this. So it's going to look something like this. So this is the crossing, this is the crossing, and these two are cusps. So the smallest, this is the red circle right here. And this is actually not a cellular decomposition. I have to do something more because this is not a two-cell. So I've got to throw in that. Okay, so that's a cell a legitimate polygonal decomposition of the projection of my Lagrangian all the way down to the base. So this is blue. Red, and then I threw in 2 extra white ones. Oh, I'm sorry, no, that's actually blue. This is blue. I only threw in 1 extra white one into my polygonal. Okay, so, and then I have to make some choices for the boundary. And let me just give an example of how one of these differentials might look like. So let's say that this is like C2, C1, C2, C3. This is like B1. This one's B2. And B4, and B3. And all the way inside. And if I wanted to look at the differential of D2, DC2, so so I have A here. So I'm gonna choose. Let's choose the same initial and terminal point. Then it looks something like AC2 plus C2A plus, okay, I'll write these down and then I'll explain them in a second. So basically, I just have to look at the boundary of this thing. Hopefully I got this right. Okay, so we go around B3, then we go back on B4, then we go up on B1. Now B1 is only a 2 by 2 matrix because this blue cusp edge does not contribute to its dimension. So I have to add a column of zeros. Similarly with B2. B2 is also a 2 by 2 matrix, so I have to enlarge that. But B3 and B4 are the correct dimension. They're 4 by 4 matrices. C is a 4 by 4 matrix because there are 1, 2, 3, 4 sheets above the 0 cell. This is 4 by 4, and this is 2 by 2. Becomes 4 by 4. Okay, so it's a complicated differential. You can see how many generators there are, but it turns out that with a sort of, there's this easy technique of reducing. So morally, if you see something like this, you can say that the DGA is stable tame isomorphic to something like this. This is called a simple homotopy equivalence. If you can do a simple homotopy equivalence downstairs, you can kind of replicate that for the DGA upstairs. And so with some simple homotopies, you get that the DGA, so with some of these moves, you get that the DGA has 3 generators. X minus 1, y, z, 2, and dx equals x plus y, x times y plus y times x. So the upshot is that not a Legendre isotopic to the unknot. So that's a hard question. I mean, oh, well, okay. So in this case, I've got, okay, so for example, I have, let's see, how do I say that? Well, okay, so y is not in the image. So we definitely have at least 2 generators in degree 2. Compared to only 1 generator in degree 2 for the other one. But honestly, it is actually maybe this is since you're asking now, maybe this is worth mentioning. Practically speaking, there's a much better way to compare DGAs, and that's to compare pieces of the DGAs, their linearizations. So maybe I should just mention this. I kind of wanted to do this earlier, but never really had the time. Is it? Maybe I don't have the gradings right. Let's see, what did I write down? Oh, well, first of all, this can't be right. Yeah, x can't be in the image of dx because of the upper triangular, the triangular properties. Right. But this is degree minus 1. Yeah. So let me just, since this is kind of, it's not a totally satisfactory question to when are two DGAs isomorphic, and an easier thing to answer is when are two things that come from the DGAs equivalent. And so maybe I should do this now. So recall that epsilon, an augmentation, is defined by a DGA morphism. Okay, and you can check, and this was kind of, I kind of rushed this into one of the homework problems. If you define, okay, so we can write any DGA as the summation of dKA. K goes from 0 to whatever. Most of these will be 0 after a finite amount of time. Where dk of A is all the words of length k in this element of the algebra. So now, if epsilon is a DGA, we can define, given an augmentation, not a DGA, an augmentation epsilon, we can define a tame automorphism phi epsilon by, on the generators, by phi epsilon of A is A plus epsilon of A. Okay? And with this tame automorphism, we can pull back the differential. Well, consider the differential d epsilon, which is phi epsilon d phi epsilon inverse. Maybe it's the other way around. Yeah. Okay. Then I claim that epsilon in an augmentation, if and only if the 0th word, when you write this out, is 0. And so if the 0th word is 0, there's no constant terms, then if you look at the square of this, and you write this down, I goes from 0 to n goes from 0 to infinity. And if you write this down, so if, then since this is true, we get that this is true. The linear differential is 0. And so we can define the linearized homology, the epsilon linearized homology of this DGA by taking the homology of this, where here we're thinking this is a chain complex. Yeah, maybe I should say that. right? Where this is the homology of a chain complex, not the homology of an algebra, because we have this linear term, this linear differential squares to 0. And this is something that's much easier to compute and compare to all of the computations all of the applications of the DGA that I talked about in lecture 2. Those were just with linearized homology. And all the computations in lecture 3, those are just with augmentations. So it was always, as opposed to actually looking at the full DGA and the, this linearized homology, of course, has structure on it, basically because it's dual to an A infinity. But, okay. Isotopy. Close. So it's the set of linearized homologies that's independent, because I could change my Legendrian and suddenly new augmentations would appear. So you look at, there's one linearized homology for each augmentation, and sometimes two augmentations give you the same linearized homology. So you write down the set of linearized homologies, omitting replication, and then that set is an invariant. And it's often just one, but not always. Well, okay, so it depends what you mean different augmentations. So if I take two Legendrians, so Legendrian isotopic, right? So is there a way for me to identify the generators here with there, or is the isotopy more drastic and has some stabilizations and such? So if there is a way to identify the generators, like it's just tame automorphisms, then there's a way to identify the augmentations, and then there's a way to identify the linearized homologies, and they're all going to be just all isomorphism. And right, yeah, yes, for Lagrangian, but it's not the front that I know of. Well, okay. So, yeah, so in the front picture, if you, actually, that might have been a way to illustrate this, the swallowtail. Notice that the swallowtail is the trace of a Reitermeister 1, and the trace of a Reitermeister 3 is also a singularity. It's going to be a triple point of 3 planes. So the traces of the isotopies in 1 dimension lower produce the singularities in 1 dimension higher. Produce some of the singularities in 1 dimension higher. So there is this kind of natural thing. But there are other singularities that, well, at least in dimension, for like a 3-dimensional Legendrian that is not a trace. Okay, but that's not exactly what you're just talking about, right? So there's also another statement that, in the Lagrangian projection, we had this move. We just had Reitermeister 3 and 2, right? So for in higher dimensional Lagrangians, you just have this move. But moduli space can still change for other reasons. You have other things that can change the underlying moduli spaces you need to consider for your invariants. But just from the point of view of maybe non-moduli spaces, yeah, this is the only thing. The creation of two, the higher dimensional version of that. Okay. All right. Maybe I'll skip this part. Well, I'll make it as a vague statement. I'll skip it. All right. So let me go to I've got 20 plus 5 minutes remaining, so let me try to talk a little bit about the second part of the talk. Okay. So we've talked about augmentations quite a bit, and sheaves. Although now I know I'm not going to get to sheaves. So we talked about augmentations quite a bit, and I will say just one pitch, because this was almost in the end of the last talk yesterday. So there is some people, some symplectic geometers and some physicists, string theorists, who are working on augmentations for knot polynomials, and they have a kind of conjectured duality between the augment that basically you look at the knot contact homology of a knot, you look at the set of augmentations there, you come up with a polynomial, you come up with a variety actually in a polynomial which solves it, and this is conjectured to equal to, I guess this is like on the B side or something, conjectured to equal some other kind of polynomial coming from the Chern-Simons A side. Okay, so generating families. Maybe the best way to motivate at the very end, yeah. At the very end. Although he didn't have a, if he'd maybe gone one step further, I think. But yes, it was that, it was this conical Lagrangian, and yeah. Anyway, so and augmentations are used elsewhere. Generating families, maybe it's best to just kind of, well, I don't know. Let me just give you the definition. Okay, so a Legendrian L has a generating family or generating function, it's sometimes called, if there exists in the generating function. So it's not a function on x, it's a function on x cross some new kind of fiber coordinate where n is perhaps big. And I'll put in a little coordinate eta for that. Has a generating family f if I can write L as the set of points in my one-jet space such that now I look at where the fiber coordinate partial derivatives are 0. I set my y coordinate equal to the partial derivative of x at that coordinate. And then z is the value of the function. So let me give an easy, straightforward example. So for example, if I have J1 of x is the one jet space of S1, then here's my front, here's J0 of S1. Okay? And I could just take a Legendrian that looks like this. So let's say L, here's pi front of L, which is where L is the one jet of a function. Then F is my generating function. It's going from x cross r, and I actually didn't need anything. It's not really a family, it's just a single function. Family denotes the fact that I kind of have a family of functions parameterized by n. I think of this single function as a family of functions. So here I didn't need anything. But supposing I had something like this. So I'm just going to Legendrian isotope this guy, and I'm going to add a little Reitermeister 1 move here. Okay? Now I can't write this as the graph of a function because it would be 3 to 1 here and 3 to 1 there. I can still write it as the graph of generating family of functions, where basically, and remember the right, maybe, you know what, it might be easier to see this. Let me draw it in the Lagrangian projection. So this is now x. This was always x. Here this was z. Now this is going to be y. Okay, and it's going to look something like this. That's the equivalent of a right armrester 1 move. Something like that. So I need a family of functions. Sorry, it's actually parameterized by not this, parameterized by this. That's actually the, sorry. Yeah, just using the wrong thing for the parameter. I need a family of functions whose critical points, fiber-wise critical points, give me these y values. So yeah, so think of it as a family parameterized by x. How can I do that? Well, over here, I just want one critical value. Over in the back here, or here. But here, I want 3 critical values. This point, and that point. So over here, I need to have 3 critical values. So it's basically, it's going to be a parabola where at some point I have a birth of 2 critical points, and then one of them grows. Maybe these 2 are born, and then these 2 cancel later and become the parabola again as I go around my circle. And if you graph the critical points, you'll see this graph. Or maybe let me try my standard unknot one. So here, yeah, I'll do the front projection. So here, this is not equal to the one jet of some function, because I've got, you know, obviously, I can't write a function on R whose z value is this, and whose derivatives are y. But I can introduce a family of functions where here I have no critical points. It's like a cubic. Here I have a cubic singularity. Here I have 3 critical points. 2 critical points. And then 2 critical points, 1 critical point, and back. So this, if you think of this as this is going to be my generating family. On R1x cross R1, this is eta. So it's a family of quadratics. Okay, so this guy has a generating family. Okay, so that's kind of what a generating family is. And since I mentioned linearized homology, I will say there's a conjectural relationship between the two. So there's a theorem that for Legendrian knots, let's see, so L sitting inside the one jet space of R1 has a generating family if and only if its DGA has an augmentation. And moreover, the linearized homology an augmentation generating family F if it only has an augmentation epsilon, the linearized LCH using this augmentation equals the relative homology defined by F, by level sets of F. Level sets, let's say, I'm going to be a little sloppy here because it's not really the function, it's the difference function, but by level sets, I don't know, 0.1, that's greater than 0, some small number, smaller than the smallest positive critical points of F, and infinity. Level sets of F at that. So I'm definitely like not being totally truthful here because I have to do one more thing to the function. But roughly that's the case. So, so this is an entirely holomorphic curve defined invariant, and this is a totally Morse theoretic defined invariant. I don't know if you did Morse homology last night. Did you do Morse homology? Okay, so I'm basically looking at the Morse homology coming from F. Relative to an upper and lower boundary. Okay. So again, the natural question is, how true is this in general? So it's a theorem, at least in one direction, that this is true. Well, generating families imply augmentations is true for surfaces. And to go the other way, we don't quite have a generating family. We have what we call a combinatorial generating family. Where here we're kind of looking at a family of Morse complex and maps induced on them. So chain maps between them and chain homotopies and kind of stuff you need for when you're studying a two-dimensional family of Morse complexes. A two-dimensional family. So I'll like that. Okay. So I got 7 plus 5. All right. So let me just give one. I'll just finish with one step in this proof, and that will hopefully then lead to the connection of this with sheaves, or microlocal sheaves. So I can get at least to that. So to prove this, you need to define a chain homotopy data. Define what I'll call chain homotopy data. So basically, I'm going to take this algebraic topology I was mentioning in the formula for the differential, and I'm going to use the augmentation and actually turn it into, I'll linearize it. Okay, so yeah, so let's fix an algebraic map epsilon. It doesn't have to be an augmentation yet, even though I'm calling it epsilon. And at 0 cells, E0 alpha, we let define a vector space V alpha to be, let's say it's Z2 graded by all the sheets above E0 alpha. Okay. And so we're going to build the following thing, which is not which is part of what should be a chain homotopy data. Okay, so again, we have the cells. We have A minus, B, A plus, and then something like a 2-cell. Okay, and we're going to, for each of these cells, we're going to consider a matrix. So here, it's the matrix epsilon applied to A. Again, epsilon is a map on the algebra, so it's also a map on the generators, which look like the algebra. This is a script A. And this is just a matrix of elements in the ground ring. And here we have another matrix of elements in the ground ring. And here we have a third matrix of elements in the ground ring. Okay, and then for each of these cells, we use this matrix to define a linear map. So in this case, our linear map, I'll call it D alpha, because this is the alpha cell, say. And this is the beta cell, and this is gamma cell. Our linear map will be just look at the algebra map defined on this generator. That's a coefficient in the ground ring, and put that in front of this sheet. So this is a linear map from V alpha to V alpha, where a V alpha is generated by the sheets that sit over that 0 cell. Here we're going to define another linear map from V minus to V plus. So here I have a vector space defined over this 0 cell called V minus, and a vector space defined over this cell called V plus, generated by the sheets that sit above minus and plus. And we're going to define it by F beta of Si equals, well, first you have the Kronecker delta plus epsilon times that. And then finally, I'll use this letter because this is what we use. So let's suppose I have an initial cell and a terminal cell, and I have these maps. This is exactly as we were doing in the sample differential. So I have these maps for each one cell. Not that matters, but we're going to define this map by summation C gamma ij. Look at the augmentation on the 2-cell Sj. So then, this is an algebra map. Now it turns out that epsilon as an algebra map is an augmentation as a DGA map if and only if epsilon d is 0. So what does that translate here? So epsilon d a is 0 if and only if d alpha squared is 0. Epsilon db is 0 if and only if f beta is a chain map. And epsilon d applied to C is 0 if and only if K is a chain homotopy between this family of maps and that family of maps. So basically all I've done here is I've kind of formalized this, what should look like algebraic topology, into actual algebraic topology. And so this is kind of the main ingredient. You can see automatically you have an augmentation if and only if you have this so-called chain homotopy data. And then it's more work to show that you get a combinatorial generating family, which is basically like a generating family but missing some information. So it's going to go buzz in about 23 seconds, just to warn you. Okay, so what do I want to end with in the remaining 8 seconds plus 5 minutes? So I'm just going to write one picture down and then just say a few things. So there's a there's a conjectural relationship between sheaves generating families and augmentations for a given Legendrian. And by sheaves, I mean, I'm not going to define any of these words, but if you know any of this means constructible sheaves whose singular support is the Lagrangian cone over the Legendrian. And there are various states at which these things are proved. So for example, in dimension 1, there's a result that says that there's an A infinity category here and an A infinity category of sheaves and an A infinity category of augmentations, and that they're equivalent. Here, I've just mentioned this one result. You have an augmentation if and only if a generating family for knots, I only admit, but there's an A infinity category statement for that for knots too. And so the only thing I want to say is that basically, for the cases of surfaces, an augmentation is clearly a chain homotopy data. It's formula. And if you were to unravel what a sheaf was, actually really it's the derived category of sheaves, but if you were to unravel this is almost apparent. Now I can't really motivate sheaves because it comes from a branch of math that I don't know anything about, but other than that one result last time that Vivek Shende did showing Legendrian knots are Legendrian isotopic. Sorry, knots are smoothly isotopic if only if they're conormal lifts or Legendrian isotopic. He did that with sheaves. But anyway, so I will end it there. So at least I got to mention the word sheaf. So. Sorry? This triplet thing? Yeah. Okay, so for Legendrian knots, there is an A infinity equivalence of A infinity categories here. And I believe here, I think. I mean, they're certainly much stronger than what I wrote down, just in existence, if and only if. For certain surfaces, basically these are, what are they called? Hyperelliptic surfaces. Basically, you take like a planar graph, a non-planar graph on a surface, and you can build a front out of it, out of two sheets. Truman and Zaslow verified some kind of A infinity equivalence for those special cases. There are definitely various groups of people working on, right now, on different parts of, in different dimensions. So.
Are there other questions? Actually, I have one probably related to this thing. That is augmentation.
Oh.
Yeah, this chain homotopy data is related to the augmentation thing that you explained.
Yeah.
But this is not something that one expects in algebra, right? If you just have like a DGA with an augmentation.
No. Yeah, it had to be that specific formula of the. Yeah, this is not in. This. Comes from the formula for the differential in the first place that looks algebraic topology. Yeah, in general,
okay.
I mean, it could have, the way I wrote it, there was basically just these quadratic terms that represented the homotopy pieces. But you could, a DGA in general could have lots of words of arbitrary length.
Okay, if there are no other questions, let's thank Mike for a nice set of lectures.
Thank you for hosting this.
So the next talk is going to be about 11:30 and for those